everything that called MPI barrier during the course of your run all gets lumped into this, okay? So then that will be the maximum, that's the total time spent by all the calls in MPI barrier. So then after that, at some point down the line, you'll see a call path, and that will give you specific instances, specific calls to this function and how much time was spent. And so this is the thing that makes it easy, is if you can see, okay, all of my time in MPI barrier, pretty much most of my time, almost all of it, comes from this one call. And so that's where I got to look to figure out how to overcome that, and maybe code things differently so that I don't need a barrier there or what have you. So that means that you don't have to worry about all the other places, if you have a lot of them in your code, that you're calling this function. So there's on this list, I don't think there's any others, but you see it's not the total time, so there are other calls to this function, but this is chopped off because it goes on forever. So, but this is the value. So when you go to do a trace and you create a selective instrumentation file, then you're going to want to include this path. Basically, you want to include these functions that make up the path to that MPI barrier call. Or you may not need the very topmost. I mean, you may be okay getting just a couple of levels above it. But you'll want to include the major routines, and the routines that call them are the ones that you're going to want to selectively instrument with tau and then go and do a trace. Okay, there's a question? Was there a question at one of the sites? Okay. Yeah, go ahead and pull me back if something's not clear. So I'll try to show some examples that will also be helpful. So, okay, so we've got, so that's the basic point of this, that you can also toggle this. So there's just some instructions here that there's a preferences where you can tell it to show the source location. So I'm not showing the source locations here for space mainly, but you can toggle that on and off and tell it to indicate to you where in the source this call is being made. Okay, so any question on that? So, as you prepare to do a trace, you would look at information like this, find those important functions and the ones that call them. And so now, so generally what you do, so when we made our first selective instrumentation file, there was, we were telling it which routines not to include. So it was like begin exclude list, and then you list all the functions, and then you say end exclude list in that file. So anything that was not in the exclude list was instrumented. But now when we do tracing, so just excluding a handful of functions, that may eliminate a lot of the overhead, but it's not going to help you much when you do a trace and you have to trace still 1,000 functions, which is going to multiply the amount of data that's created by 1,000 times. So now you want to reduce it so that you just have a handful of functions that you're tracing to minimize the amount of data you're producing, and also to make it easier to comb through what's important when you have this trace. So now instead of having in the selective instrumentation file, you would have, instead of an exclude list, you'd have an include list. And so you would say begin include list, and then you just list the functions you want to include. And if that's all you have in your selective instrumentation file, then tau will, by default, only instrument those files that you specifically included. And so you can reduce the size of the trace substantially in that way. So that's the main preparation when you're compiling, is that you need to create that selective instrumentation file with that include list. You point that tau opt to that, Or yeah. So again, so you set this tau options environment variable, and within that you have this option set point to that selective instrumentation file. Now you compile your code with tau as you normally did, and you'll only now be tracking a handful of functions. So, okay, so then once you've done all that, at runtime, you just set this environment variable. So if you don't set this, it will default and just do a profile on those functions. But if you want to do a trace, then at runtime, you set this environment variable, and then away you go. And it'll get a time-resolved performance information on each process and each function. So that's also going to be, you'll have to think carefully about how many processors you need to run on. But also, since it runs in time, you'll want to make that run as short as possible. But since you're doing a time-resolved thing, you can really make a trace pretty short. You may only need a handful of iterations to see the information that you need. Okay, so then you'll be able to see the duration of individual MPI calls, and you'll be able to see how the dynamics of your blocking calls. You can see maybe if you're posting certain calls where you're blocking calls, you're posting too early, and so everything has to wait. And then by looking at these dynamics, you can look at where are there opportunities you're missing to overlap the computation and communication that's going on in your code. So again, in this cheat sheet, there's some information about after you do the trace, what you do with there's a bunch of files that are generated, and there's a few commands that you issue to put those into a format that you can look at. And then there's a trace analyzer, or at least a trace viewer analysis tool, which is free, which is included. This is the other thing you get when you installed that tau distribution on your laptop or workstation. It also comes with this jump shot tool for analyzing the trace. And then you'll have, so here down the left, you'll have the different processes. So there were 16 processes here. And then there's also a color-coded list of all the functions, which is not shown here. And so each function has its own color. And if you hover over it or right-click it, it'll tell you what function it is. But here, just the thing to note is that you can see the pattern in these calls. So we're in the middle of the MD loop. And so these are the different time steps. So here you can see there's 3 time steps that we're looking at in this trace. And you can see the length and duration of each one of these functions during each of these time steps. And then there's other things you can do. You can actually have tau keep track of every message that's sent. And so you can track and look at individual messages and look at all the detail you could possibly hope for. But you can also narrow this down. So there's ways to, in that function list, you can tell it whether you want the function to be visible. So you can get rid of a bunch of functions that you don't want to look at, and then you can just narrow it down to the things you're interested in. And this is where profiling and tracing can sort of play, can be useful. And if you do both with profiling, you might, so here, remember, we did a profile and we saw some load imbalance, right, in this particular function. So now if we do a trace on these functions and we see, where this MPI barrier is called, and we see where this other function is called. So now in our trace, we can actually take a look at these 2 functions. So here in brown is our compute function, and then in pink is that MPI barrier. And so you can see the pattern of what's going on here, and you can see that, you can see if there's a pattern that repeats across iterations. And so, for example, this one is on node 0 is always starting, is always getting ahead of everyone else. It's starting much earlier than the other calls, and some of these are consistently shorter than others. And you can see, but this last one, usually it always starts last. And so this is the one you can see here that's holding everyone up. So you can see these type of patterns in your code. So I already alluded to several times, I guess, some of the issues with doing tracing. That it can generate an overwhelming amount of data, especially if you go to really high processor counts. So you have to be very selective in your instrumentation, just get a handful of functions. And then you want to make sure you can isolate that computational kernel, that section of the code you're interested in, and just do the trace for the minimum number of iterations. So if you can just do a few iterations on a few functions, then tracing can be scalable. You can do traces on thousands of processors. Even with all those things, even when you par it down like that, once you get up to thousands and processors, you're going to generate really big files. So that's just something that you're going to have to deal with. But you can at least make it possible. And if it's important to do tracing at that level, you can find ways to make it feasible, even if you have to then deal with you'll be dealing with some pretty big files. But there is this other issue of once you go up to thousands of processors, trying to sort of manually analyze a trace of this complexity. Like I said, using the profiling can really help you there, and it's drilling to help you to know exactly where to go in the trace to look to find, or at least narrow down where you need to go to find what you want to find. But still, it starts to become it can become pretty complex pretty quickly. So there are tools out there that try to reduce this complexity and to automate some of these things, to do some automated analysis of traces. One of these is one of those tools that's part of this point project that I mentioned. It's called Scholastica, and it does some automated analysis of tracing. So that's something that it's very much a new tool, or it's in very active development. And so getting it to work with different codes, sometimes requires working with developers and things like that. But it's maturing, and we've used it for. I'll show you just a snapshot of one of these. Well, there it is. So it's something that you might want to consider if you have to do a lot of trace analysis, I guess, bottom line. And try to automate some of that. Or even if you just want to give it a shot and see if it can point out anything interesting that you may not have picked up on. So it's worth a shot to get some of that automatic analysis and looking at some of those common pitfalls. There's also, this is free, there's also a very good product called Vampire, which is not free, but it is available, I think, on Big Red, on the TeraGrid. So if you can get and one of the nice things about Tau is that it is this Swiss Army knife, and it sort of interfaces with everything. So not literally, but it seems like almost everything. It can create an output file which can work with this proprietary Vampire software. So you can create a trace in Tau and then analyze it with Vampire. You can also create a trace in Tau and analyze it with Scholastica. Some of these may require like a special option in the make file when you build it. So they are reducing the number of options that they require in the make file. Every time they release Tau, they've been frequently cutting out the things you have to actually compile with and turning those into runtime options. And so that's nice. That's becoming better and better. But on some of these things, you still have to specify, or you still have to have a specific option within the Tau make file to generate the